Alrighty, so we are going to do lesson 4 this week. We're talking about measurement data, different ways to display it. We're also going to talk about different ways that you can describe it. So first, let's just kind of talk about the different ways that you can display measurement data. So let's remember, first of all, that our measurement data is going to be anything that's quantitative, so anything that has a value along with it. These will be anything like numbers, amounts of anything, a size, anything that has numbers along with it and values. And so this is an example of a measurement data display. This is called a stem and leaf plot. And basically all this does is kind of split up your data into two different columns. And then we have our stem is going to be this 1, 2, 3, this 1, 2, 2, 3, 3. This is going to be our stem. And then all of these things are our leaves. Okay, so that's where that comes from. So the stem is telling us the tens place. Okay, and then our leaf is telling us the ones place. So for example, if we were to try to read this, if I want to read this number right here, this would be 37, because if you do, the 3 is going to be the tens place, so that's going to be 3, and then for the ones place, that'll be 7. Let's say, and you can even just choose something out here. If I wanted to figure out what this number was, all I would do is first go to my stem and see I have 2, and then in my ones place it's a 4, so that would be 24. So yeah, that's basically how you read it. All of this is saying over here, it's basically counting towards the median. So this 9 is saying, if you would count these out, that there's 9 different leaves here. And then if you add these, then it's going to get to 25, that kind of thing. So, but yeah, so that's basically how you read that. And that is an example of a measurement data display. All right. So next we have histograms and dot plots. So I grouped these together because they're pretty similar in the fact that the way that they display data in this like frequency way. So here with our histogram, you can see that it's a graphical representation of our quantitative data. Remember, all these are for quantitative data. And basically what it's doing is showing you how high the data goes in comparison to each different part there on the x-axis. So in this case, it's basically showing the frequency of a certain age. So how frequent does that age happen? And frequency of it is shown by the height of the bars. And then also keep in mind that bars do touch in histograms. In bar charts for categorical data, then the bars are separated. But here in histograms, we do have them touching. So that's an important thing to keep in mind. What else? So yeah, so a good advantage to these is that you can put a bunch of data in, because you can make the y-axis anything you want. It can go from 0 to 1,000,000, but you can still show it within those bars, and that's still okay. But you can't show individual observations like a dot plot can do, because for a dot plot, each individual observation is represented by a dot. It's still shown in the same way that you have your x-axis, and then the frequency is represented, by the height. But in this case, it's not a big group in a big bar. It's each individual thing. So that's why I'm saying if you, it's a disadvantage to the fact for dot plots that you can't do for large data sets, because if you did and you had like 1,000,000, inputs, you would have way too many dots. So that's when you would want to switch over to a histogram, so it makes more sense and it's concise. So yeah. Okay, so this is just a way to kind of talk about skewedness. So when we talk about something being skewed, that basically means that the spread is a little bit different on one side in comparison to the other. So to start off, it's important to understand symmetrical, what symmetrical is in general. So that's basically, it's also known as like a mirror image. So it's basically just showing you here that, it's the same on the left as it is on the right. But for these other ones down here, you can see that the left and the right aren't the same. So for this first example right here, for skewed to the left, the data down here on the left side is way more spread out than on the right. So that's why it's skewed to the left, because our data is more spread out down here. And it makes sense because our mean is our smallest thing, our mode is the largest. So remember, our mode is the most commonly occurring number. So if you think about it, it's going to be the highest point in the graph, whichever one happens the most. Remember, your frequency is your height. So your mode's the highest, your mean is the lowest. That means that the average is a smaller number in comparison to the mode. So your average is a bunch of small numbers, hence why there's such a spread down here. And then skewed to the right, it's the complete opposite. You see your mode is the smallest here. It's going to be the highest point there. And then your mean is going to be the largest in terms when we're talking about being skewed to the right. Alrighty. Okay, so then we have box plots for more measurement data display. So box plots basically are a way that we can talk about percentiles, which we'll get into in a little bit. But yeah, box plots are a graphical representation where we can represent our percentiles within a box, and then we have those lines out there to represent other quartiles. And that's how we split it up. We split up our box plot into quartiles. So there's technically 4 different parts to a box plot. And side-by-side box plots, the only difference between those and a normal one is just that you'll have, like, if you have like 2 different groups that you're comparing. So in this case, we have men and women. So you're taking a categorical variable and representing it on a box plot. Remember, box plots are for measurement data. So here we're talking about age. So that's our measurement data. But if you have a side-by-side box plot, you can compare 2 or more groups. You can put multiple box plots on there. Those can be categorical because those are just, different labels. So they're comparing men and women in terms of age, and that's how you look at those. Alrighty. Okay, so the 5-number summary. This is basically how we are able to kind of summarize our data in a way that makes sense. And you can easily see the 5-number summary on a box plot. That's why these are important. So if we draw out a box plot here, I'm just going to label the different parts here. So we have our minimum down here. That's going to be the lowest end, and then our maximum, the greatest value. And then the quartiles are in here, okay? So this is going to be our Q1, here's Q2, and then here's Q3, okay? So we have 3 quartiles. And like I said, we have 4 different parts of the graph here. So we have this first part, second, third, fourth, okay? Remember, our Q2, this line in the middle here, is always our median. So our median is resistant to value. So basically, it'll keep it, as long as it's in the same position, it's going to stay the same. It doesn't matter if you replace the last number. Like if your last number is 10, you replace it with 1,000. As long as it's the same amount of numbers, your median will stay the same. So yeah, those are the different quartiles then. So if we think about quartiles, quartiles like quarter, so 25, that's a way to think about it. So here our Q1 is in the 25th percentile, which that means that 25% of the data lies at or below Q1. Okay, so to give that a visual, this is going to be 25% of our data, okay? Because 25% lies at or below Q1. And then next we have our Q2, which is going to be our 50th percentile, which that makes sense because it's our median. So that's the dead center. So that means that 50% of our data lies at or below Q2. So technically, if you think about it, this is another 25%, but together, this is going to be 50%. And then Q3 is our 75th percentile. 75% of our data lies at or below Q3. And just keep in mind that we have our, back some of this up. We have our interquartile range, which is this area in here. So our normal range is just from our minimum to our maximum, so the entire range. But this is our interquartile range, so it's the range within our quartiles. That's where it gets the name from. So this is going to be our IQR. And the equation down here is right here. So you take Q3 minus Q1, and that's how you get your IQR. So that's going to be the range within the box. Okay. Let's keep going. Okay, so we're going to do some reviews now. So if you're watching this back, go ahead and we'll read over the review, pause the video so you have time to think about an answer, and then go ahead and resume and we will review it. Okay, so this first one says, if a data set is skewed left, which of the following is a preferred measure of center or location of the data? So go ahead and look these over, pause the video if you're watching it back, and we will go over it then. So let's first, to review this one, let's discuss what a left skew would look like. So remember, our left skew means that the data is more spread out on the left side, okay? So it's going to look something like this. So, and then it says, what is the preferred measure of center or location of the data? So in this case, if we have something that's skewed, remember that we were talking about how like our mode is going to be the highest right here. It's like going to be our mode. And then our mean is going to be down here. But what's always the same? Remember our median. Our median is always the same because it's resistant to no matter what happens down here and down here, the median is always going to stay the same as long as the position of the numbers stays the same. So in this case, our answer is going to be A. We want to choose our median as a preferred measure of our center because it's resistant. So it's less affected by outliers. So that's why, because usually if you have a skewed data set, it is possible that you have an outlier. So you want to use a resistance statistic for your center of your data, because then it won't be affected by outliers. Like I said, as long as, so you know, if you had a data set of like 1, 6, 14, 21, and 22, 14 is going to be your median, okay? But, and this is what I mean by resistant, okay? So if you wanted to change this 22 to 1,000, your median is still going to be 14 because you still have 5 numbers. They all stay in the same, like it's 14 still the middle position, so that's going to be it's going to be resistant. That's what we call it. All right, resistant. Sorry. All right, cool. So let's go over the next one. Okay, so mom was told at her son's 1-year checkup that his height was at the first or lower quartile. What does this mean? Let's go ahead and pause this if you want to go ahead and try this one, then we'll go over it. Okay, so remember when we talk about quartiles, so the first quartile, so Q1, remember that's in our 25th percentile, okay? And percentiles, basically they're saying what percent of the data is at or below what you're looking at. So in this case, if we look at, if her son was in the 25th percentile, that means that 25% of 1-year-olds are at or below her son's height. So that means that 25% of 1-year-old boys are shorter than her son. So this is going to be D. Because if we draw this on a box plot, and this is going to be our minimum height, and then this will be our maximum. And then here we have Q1, so this is our 25th percentile. This is representing this right here, okay? So these are the people that we're looking at. So all these people are below his height because he's in the 25th percentile. So he's right at the cusp right here. So 25% of the 1-year-old boys are shorter because they're down here. This is 25%. So our answer is D. Okay. All right, for number 3, so it says, for a symmetric data set, the proportion of the data that falls at or above the mean is about what? So this is where you want to think about, you know, the percentage of the data, how much is where. So remember that our mean is our average. So if we have our average, that's going to be our dead center. That's, you know, it's symmetrical on either side. So if we draw out a symmetrical, this is like a normal curve. If we draw this out, this is saying, you know, it's the same on this side as it is on this side. It should be like a mirror image, remember. So if you think about it, this entire thing is 100%. So if it's same on one side as the same on the other, then that means that we have to take 100 and divide it by 2, and whatever, we have to have the same amount on one side that we do on the other, and the only number that works for that is 50%. So our answer has to be A, and it says falls at or above the mean. So if this is our mean here, the center, then that's going to be the 50% that's falling at or above. So our answer is A. Alrighty. All right, review number 4. So which of the following statements are true? Is true. So A says if a data set is skewed to the left, that means that there's bias in the results and the data are lower than they should be. B says if a data is skewed to the left, then the higher values are more spread out than the lower values. Or C, if a data set is skewed to the left, then lower values are more spread out than higher values. So go ahead and think this one over. So if we remember what a skewed left data set looks like, once again, it's going to look something like this. So C is the answer because it says the lower values are more spread out. So these are lower values. So these are more spread out. And then the higher values. So these would be the higher. And you can see like they're more tight in here. So this is basically just the definition of a skewed left data set. So our answer would be C there. Okay, cool. All right, so next group review for lesson 5 will be next Thursday, the 21st at 8:30. And yeah, I hope you guys have a great weekend.